Okay, this is lesson 4.1, Properties of Exponents. First of all, we need to understand exponents, which is a mathematical shortcut for demonstrating repeated multiplication. Right, so the exponent terminology represents the portions of the expressions and what occurs. So here we have a term with an exponent. The y is the exponent, and the x is the base. The exponent tells us how many times the base gets multiplied by itself. So for example, 5 to the third, that's not 5 times 3, that's 5 times 5 times 5. So we multiply 5 3 times, and that gives us 125. If you have more than one exponent expression with the same base, this is known as common bases. X to the third and x to the eighth have common bases. The x is the common base. Okay, the properties of exponents are going to hold true for all real numbers. So this includes variables, integers, fractions, and decimals. And here we have all of the properties. And you'll want to write these down so that you can learn them. A zero exponent, so anytime the exponent is 0, it equals 1. So any number to the power of 0 except 0 equals 1. 0 to the 0 power is undefined. We can't really do 0 to the 0 power, but everything else to the 0 power equals 1. So if you had 50 billion to the power of 0, it equals 1. Negative exponents are illegal. We don't have negative exponents, so we take the reciprocal. So x to the negative y, we want to flip that over and make it 1 over x to the y. Product of powers. So if we have a common base, x to the a times x to the b, that equals x to the a plus b. So we add the exponents. And then if we're dividing exponents with a common base, we subtract them. So x to the a divided by x to the b is equal to x to the a minus b. Now if we take an exponent and we raise it to a power, so you'll see the difference here, we have two bases. Here we have one base with two exponents. When that happens, we multiply the exponents. So x to the a raised to the b is equal to x to the a times b. If we have two bases and one exponent, we distribute that exponent to both bases. And so you have xy to the a is equal to x to the a, y to the a. Same thing if I have a quotient, so basically like a fraction or division, I'm going to distribute that exponent to both terms, and I have x to the a over y to the a. And then if we have any common factors, we will simplify that, and we'll talk about that a little bit later. Now, a rational exponent. This is an exponent that is a fraction. Rational numbers are expressed as fractions. So if we have an exponent that is a fraction, the numerator becomes the exponent underneath a radical, and the denominator is what type of root we're taking. So if this was a 2, we would take a square root. If this is a 3, we're taking a cube root, etc. Okay, examples of each of these properties. Okay, for the 0 exponent, if I have 321 to the 0, that equals 1. If I have a negative exponent, here I have x to the negative 5th. When this occurs, I need to take the reciprocal, so I'm going to put that in the denominator and have 1 over x to the 5th. If I already have a negative exponent in the denominator, I take the reciprocal and I move it to the top, and that'll be x to the positive 3. If I have 2, 1 in the numerator, 1 in the denominator, I flip it. So x to the negative 2 over y to the negative 4th is going to be y to the positive 4 over x to the positive 2. If I have a product of powers, so here are the ways these can look. I can have a multiplication symbol between the two. This is going to be x to the 3 plus 5, which is x to the 8th. Here is another multiplication. Again, it does have parentheses, but you'll see I have two bases, not just one base. So this is x to the 6th plus 4, which is x to the 10th. And then when I have two bases, two different bases, x and y, common ones go together. So the x's are going to go together and the y's are going to go together. So I'll have x to the 2 plus 3, y to the 4 plus 2, which will give me x to the 5th, y to the 6th. If I have quotients of powers, again, this is division. Quotient means division. I subtract my exponents, so I have y to the 10 minus 3, which is y to the 7. If my larger exponent is on the bottom, I'm still going to subtract. So I have y to the 2 minus 7, which is y to the negative 5, but I'm not allowed to have that negative exponent, so I need to take the reciprocal. Now, a shortcut for this is to think of this. Why did I use y? Hold on one second. Those should have been x's. Sorry about that. Now, shortcut for this. Think of this line as kind of the tug of war line, and whatever number is bigger is going to win the tug of war. So the 7 is going to win the tug of war. So if I subtract 7 minus 2, and I know that the 7 is on the bottom, so it's bigger, I get x to the 5th on the bottom, and if there's nothing left in the top, I add a 1. So let's try that here. I have a 4 and a 9. The 9 is bigger. 9 minus 4 is 5. And here I have an 8 and a 3. The 8 is bigger, so 8 minus 3 is 5. Now I can't reduce this at all because I have an x and a y. And we'll talk about reducing a little bit later, but they have to match in order to be able to reduce. Okay, next example is a power of a power. So we have, again, one base, two exponents. So I multiply those, and that gives me x to the 12th. I have a power of a product. So again, remember we have x and a y, two bases, one exponent. So I distribute that exponent in, and I have x to the 4th, y to the 4th. Now, if there were already exponents in there, when I distribute in, I'm going to be multiplying. So this is going to be x to the 3 times 7, y to the 2 times 7, which gives me x to the 21st, y to the 14th. Next, I can have a power of a quotient. So I distribute in this 5, and I'll have x to the 5th, y to the 5th. And here I already have exponents, so again I'm going to distribute in, but I'm going to multiply. I'll have x to the 3 times 2 over y to the 7 times 2, which gives me x to the 6th over y to the 14th. And finally we have the rational exponents. That is an exponent that's a fraction. Now if my fraction is 1/2, that's going to be this 2 on the outside and a 1 on the inside, but an exponent of 1 is kind of pointless because that just means there's one x, so we just write x, and we don't have to put the 2 on a square root. Now if I do have other numbers here, the bottom on the 3 goes on the outside, so we're talking about a cube root of x squared. Okay. We have a 6 and a 4. The 4 goes on the outside and the 6 goes on the inside. Now, the 4th root of x to the 6th, there are 6 x's in here. Any 4 of them together can be taken out. We can take the 4th root of it. This is like saying the 4th root of x to the 4th times x squared. Now the 4th root of x to the 4th is x, so I can take that out, and there are 2 left behind. So what I did basically is I said 6 minus 4 leaves me with 2, and 1 comes out. And we can talk more about that a little bit later. Okay, multiple properties of exponents can be applied at the same time in the same problem. So here I have 5 to the 1/3 to the 3rd. I'm going to distribute that in first, and I'm going to get 5 to the 3/3, which is 5 to the 1, which is simply 5. Or when I distribute in, I could end up with 2 to the 2/6, which gives me the 6th root of 2 squared, which is the 6th root of 4. If I have 2 being multiplied together, remember we're going to add these. So I have 3 to the 3/6, which is the 6th root of 3 to the 3rd, which is the 6th root of 27. 3 to the 3rd is 3 times 3, which is 9, times 3, which is 27. Now I'm going to subtract, and I'm going to get 4 to the 4/6. So I will get the 6th root of 4 to the 4th. And 4 to the 4th is 4 times 4, which is 16, times 4, which is 64, times 4, which is 256. So I'm going to have the 6th root of 256. Sometimes we'll have non-common bases. So first we'll rewrite it as an expression with common bases if possible, and then we will apply the exponent properties. It may not always be possible, but we'll add that in there, if possible. Okay, so here's what I mean. 25 and 5, these don't match. However, 25 is equal to 5 squared. So 25 is 5 squared to the 1/3, and then we are multiplying that by 5 to the 1/3. So 5 squared to the 1/3 is 5 to the 2/3 times 5 to the 1/3. We'll add those together and we'll get 5 to the 3/3, which will be 5 to the 1, which is 5. So I was able to turn this problem into a problem with common bases because the 25 was equivalent to 5 squared. Sometimes we may have compound exponential expressions. So 81 to the 1/4, or we could have a square root of a cube root of 7. Now, while this is legitimate, it doesn't look very good. Same thing here, 81 is 9 squared, and we're raising that to the 1/4, which will be 9 to the 2/4, which will be, hold on, let me break that down even a little bit further before we do this. 9 is also 3 squared. So I have 3 squared to the 1/4. Now I've broken that down as far as it can be broken down. So 81 was 9 squared and 9 is 3 squared. Now I'm going to multiply all these together. I have 2 times 2, which is 4. So that's 3 to the 4th to the 1/4, which is 3 to the 4/4, which is 3 to the 1, which is 3. Now the other way you could have done this is you could have taken the 4th root of 81, and there are multiple ways to take the 4th root of 81, but you would have ended up with 3. And we'll talk more about this process a little bit later. Now here I have the square root of the cube root of 7. Now the cube root of 7 is the same thing as 7 to the 1/3. And the square root, remember that's a denominator also, so that would be 7 to the 1/3 to the 1/2, which gives me 7 to the 1/6, which is the 6th root of 7. Now another way you could approach this is we can go ahead and write in the 2 and multiply them together. So I have the square root of the cube root of 7. That is going to be 2 times 3 root of 7, which gives me the 6th root of 7. So that is another way that you can approach that problem. All right, so let's apply some of this. Pythagoras asked me to find the area of a rectangular garden. So first I'm going to draw a rectangle. Here's my rectangle garden. Using his amazing triangles, he found the length of the garden to be the square root of 7 and the width to be 3 times the square root of 7. And we need to find the area of that rectangle. Now remember, area is equal to length times width. So I need to find the area, and that is going to be the square root of 7 times 3 times the square root of 7. Now, if I look at that, you know what, that is a typo. Hold on one second, and I'm going to fix it. That's meant to be the cube root of 7, not the 3 times the square root of 7. Like apparently, when I typed this in here, I forgot to make that like that. Okay. So we're multiplying these together. I have a square root and a cube root. First, I'm going to convert them to a fractional or rational exponent. So a square root of 7 is the same thing as 7 to the 1/2. Here's my 1, here's my 2. A cube root of 7 is the same thing as 7 to the 1/3. Here's my 1, here's my 3. When I multiply that together, I'm going to have to add those fractions. Now, briefly, let's review adding fractions. Okay, we need a common denominator. Okay, between a 2 and a 3, our common denominator is going to be 6. So in order to turn a 1/2 into a 6, I need to multiply by 3. So that's going to be a 3/6. And to turn a 1/3 into a 6th, I need to multiply by 2. So that gives me 2/6. So my area is going to be 7 to the 3/6 plus 2/6. So that will be 7 to the 5/6. And now we don't leave fractional exponents. So that is going to be the 6th root of 7 to the 5th. Now be very careful that we're multiplying here, which means we're adding our exponents. Don't get that mixed up and try to multiply those. You'd get the correct root, but you'd have the wrong exponent. Okay, now we have a tree that is 6 1/4 feet tall. And Lynn needs to cut the tree into pieces that are the cube root of 64 feet long. How many pieces will Lynn be able to cut from this tree? So what we need to do is we're going to need to divide 64 and 1/2. We're going to divide the length by the size of the piece. Okay, so I'm going to take 64 and 1/2 and I'm going to divide it by the cube root of 64. And this is not really doable in the format that it's currently in. because I have 1/2, I have cube roots. So what I'm going to do is I'm going to take that 64 to the 1/2 and leave it the same, but I'm going to convert this cube root of 64 and make that 64 to the 1/3. When I divide, I subtract my exponents, so that's going to be 1/2 minus 1/3. I need common bases, and luckily we just did those, so that'll be 3/6 minus 2/6. So that is going to be 64 to the 1/6. That is how many pieces Lynn will be able to cut from the tree, but remember, we don't want to keep that as a fraction, so that'll be the 6th root of 64. That is how many pieces Lynn will be able to cut from this tree. And again, we will talk about how to simplify these a little bit later. Right now, getting this far is good. Okay, Iris invited 2 people to go to the movies, and these 2 people invited 2 more people, and those 2 people invited 2 more people. So now there are 2 to the 3rd people going to the movies with Iris. Now, she's planning to buy 16 to the 1/4 of a tub of popcorn per person. So how many tubs will she need for the 2 to the 3rd people? We want a common base. So I have 16 to the 1/4. 16 is 4 squared, and 4 is 2 squared. So what I'm going to have is 2 times 2, which is 2 to the 4th, times 1/4, so 2 to the 4/4, which is just 2 to the 1, which is just 2. That's how much of a tub of popcorn per person. Now, how many tubs will she need to buy for the 2 to the 3rd people? Okay, so what we're going to do is we're going to take the number of people and we're going to divide it by the tub. So I have 2 to the 3rd divided by 2, which is 2 to the 1. So it's going to give me 2 to the 3 minus 1, which is going to give me 2 squared, which is going to give me 4 tubs of popcorn. That's how many tubs she will need to buy. And those are our exponent properties.